I'm Tsuneomi Kawasaki from Tokyo University of Science. Our research interest includes the origin of biological homochirality. As illustrated in this simplified scheme, proposed origin of chirality, such as circularly polarized light, chiral surface of mineral, etc., and isotope chirality induce chiral compound with low EE. To achieve the high enantiomer enrichment observed in L-amino acid and D sugar, a suitable amplification process is necessary to reach biological homochirality. For the first time, Professor Sowai reported the asymmetric autocatalysis with amplification of EE. In the asymmetric addition of diisopropyl zinc to pyrimidine carboaldehyde, pyrimidyl alkanol, S-pyrimidyl alkanol with as low as 0.00005% EE can act as a highly efficient asymmetric autocatalyst. During consecutive reaction, the pyrimidyl alkanol isopropyl zinc alkoxide can act as a asymmetric catalyst for its own production. The enantiomeric excess significantly amplified to the near enantiomerically pure state. Because of these highly significant amplification of EE, this reaction have been considered as one of the prerequisites for the research on the origin of biological homochirality. On the other hand, we are interested in the Strecker amino acid synthesis, initiated with a report on the prebiotic synthesis of amino acid by Professor Miller at 1953. This reaction have been considered as a abiotic mechanism for amino acid synthesis. In the mechanism, condensation between aldehyde and amine forming imine, and the cyanide addition to imine form alpha aminonitrile with new chiral stereogenic center. After the hydrolysis of alpha aminonitrile yields alpha amino acid with the same molecular handedness to the alpha aminonitrile. Therefore, we focused on the generation and amplification and multiplication of chirality at the formation stage of alpha aminonitrile. The key technique of our research is chiral crystallization, that is a conglomerate formation. In 1954, having a reported first example of the total spontaneous resolution to give enantiomerically enriched chiral quaternary ammonium salt spontaneously, because these compounds crystallize in conglomerate. In 2005, Professor Cristobal Biedma reported the amplification of solid state enantiomeric excess of the chirally crystallized sodium chlorate by the vigorous stirring of the suspension with low EE, finally achieves near enantiomerically pure state. And then Professor Nordan and Blackmond and their co-workers expanded this Biedma ripening to the chiral organic compound with under the under the racemization of the solution phase, as shown here. So first, we found the total spontaneous resolution of alpha aminonitrile in the three-component Strecker reaction between these three achiral compounds, HCN, para-tolualdehyde, and benzhydrylamine, because of the this aminonitrile crystallized in conglomerate to form conglomerate. Therefore, in combination with the three-component Strecker reaction, enantiomerically imbalanced aminonitrile spontaneously precipitated, as shown here. Among the 43 repetition of the 43 experiment, we obtained D aminonitrile E in 22 times, and oppositely configured L-aminonitrile obtained in 21 times. Therefore, the molecular handedness is stochastic, as shown this histogram. Next, we check the amplification of solid-state EE. The enantiomeric excess of suspended aminonitrile with as low as approximately 0.05% EE can be amplified to near enantiomerically pure state by this heating cooling operation. When the suspension was heating to 40 to 5 degrees, when at the heating step, because this compound forming conglomerate, so the racemate is dissolved. Then the 10 to 20% of remaining residual solid, the EE was concentrated to the residual solid. Then cooling step to room temperature, the recrystallization occurred based on the concentrated EE of the remaining solid. So the repetition of this cycle, after the repetition of this cycle, we can get the near enantiomerically pure product. So in combination with the hydrolysis of alpha aminonitrile, we can synthesize the enantio-enriched alpha amino acid without decrease of enantiomeric excess. Therefore, we have demonstrated the spontaneous absolute asymmetric Strecker synthesis of alpha amino acid without the intervention of any chiral materials. This is the, we expanded the stereoselective reaction. The hydrolyzed product of alpha amino acid, alpha aminonitrile, that is alpha para-tolylglycine, can act as a chiral initiator of the amplification of aminonitrile. Therefore, in the presence, as shown in entry 1, in the presence of alpha para-tolylglycine with 97% EE, after the formation and amplification of alpha aminonitrile, we obtained L-aminonitrile with over 99.5% EE with 45% yield. On the other hand, as shown in entry 2, D-amino acid induced the production of D-aminonitrile with significantly high enantiomeric excess. Even when the enantiomeric excess of amino acid was reduced to 50 to 10, the stereochemical relationship is reproducibly constant. So L-amino acid induced the L-aminonitrile and D induced the D-aminonitrile. Therefore, we have demonstrated the L-amino acid induce their own chiral intermediate aminonitrile. So we have demonstrated the first example of the replication of chiral amino acid in the Strecker synthesis. By using these significant amplification of EE, we have reported that asymmetric HCN addition at the single enantiotopic phase of a chiral imine enantiomerically enriched alpha aminonitrile could be obtained with the corresponding absolute configuration to that of the SI phase, enantiotopic SI phase and RE phase of imine at the single crystal phase. Therefore, single crystal phase of a chiral imine oriented prochirality of the achiral intermediate imine can act as a source of chirality for the enantioselective amino acid synthesis. Next, we use the chirally crystallized achiral imine. Chirally crystallized chiral imine was used as the substrate of asymmetric vapor phase HCN addition. This imine crystallized to form chiral crystal. Then vapor phase HCN addition and following amplification of EE can give the highly enantiomerically enriched alpha aminonitrile. Therefore, chiral crystallization of a chiral intermediate can work as the efficient source of chirality for the highly enantioselective amino acid synthesis. So now we move to the today's one of the today's topic, isotope chirality. In the previous slide, spontaneous absolute asymmetric Strecker synthesis of alpha aminonitrile was demonstrated between these three achiral compounds. By introducing the isotope chirality to this compound, so the we want to make this reaction stereoselective when one of the enantiotopic phenyl group of benzhydrylamine was enantioselectively deuterated. This achiral compound become chiral, as shown here. But the chirality is solely due to the difference between hydrogen and different between the small difference between the hydrogen and deuterium. So the isotope chirality is tiny. Therefore, by using the isotope chirality as a only the source of chirality, enantioselective amino acid synthesis is challenge. As mentioned, the isotope chirality is very small. Therefore, cryptochirality was allowed in this asymmetric reaction and kinetic resolution. On the other hand, the reaction including the amplification of chirality, the isotope, the effect of chiral compound arising from isotope substitution is clearly demonstrated. Professor Mark Green reported the control of the helicity of the secondary structure of polymer synthesis by using the hydrogen isotopically chiral monomer. And Professor Major reported the synthesis of helical aggregate of this aromatic triamide compound with the isotopically chiral alkyl chain. Moreover, Professor Sowai reported the asymmetric autocatalysis triggered by carbon isotopically chiral compound. As shown, I'm one of the co-authors. In the reaction, this compound dimethylphenylmethanol with carbon isotope chirality can act as the chiral trigger for the asymmetric addition of diisopropyl zinc to pyrimidine carboaldehyde. After the significant amplification of enantiomeric excess, S and R pyrimidine alkanol with over 99% EE was obtained with the corresponding absolute configuration. Not only the carbon isotope compound, but also oxygen isotope, isotopically chiral compound, and nitrogen, and of course hydrogen, deuterium substituted chiral compound can act as highly efficient chiral initiator. So we started the synthesis of chiral benzohydryl amine, as shown here. S-benzohydryl amine was prepared by the rhodium catalyzed asymmetric phenylboloxine addition to this labeled bis sulfamyl imine using this RRR ligand. By using the same chiral ligand, RRR6, labeled boloxine, asymmetric addition of labeled boloxine to a non-labeled imine gave opposite enantiomer of benzohydryl amine. The enantiomeric excess of isotope chirality can be determined by derivatizing to the MTPA amide using proto-NMR. The experimental procedure was shown here. Synthesized chiral benzohydryl amine arising from deuterium substitution was reacted with paratolualdehyde forming imine. Then isotopically chiral imine was reacted with ACN in this solution. After the evaporation, the solid mixture of this aminonitrile could be obtained. Then this mixture was suspended in methanol in the presence of DBU, which was mediates the epimerization. Then amplification was chirality was applied. Highly enantiomer-enriched aminonitrile was obtained by the filtration. The stereochemical outcome was summarized in this table. In round 1, when S-benzohydryl amine was used, after the Strecker reaction and amplification of E, we have obtained L-aminonitrile with over 99% EE with 56% yield. On the other hand, in round 2, R-benzohydryl amine affords D-aminonitrile with over 99% EE in 53% yield. Even when the enantiomeric excess of labeled compound reduced to 55, 14, the stereochemical relationship, the same stereochemical relationship could be obtained. S gave L-aminonitrile, R give D-aminonitrile. Even when the labeled ratio was reduced by mixing non-labeled achiral benzohydryl amine, the stereochemical relationship is produced the same stereochemical relationship as shown in entry 7 and 8. This is a rationalization of the stereochemical relationship. That is a solubility difference of the geostereomeric isotopomers. Considering the Strecker reaction of S-benzohydryl amine and this paratolualdehyde and ACN, anti-L-aminonitrile and syn-D-aminonitrile would be formed. That is cryptochirality. And this solid mixture was suspended in isopropyl alcohol without epimerization mechanism in this solvent. Then supernatant was analyzed using chiral HPLC. As a result, and averaged value, the thin diastereoisotopomer were more soluble than the anti-L diastereomer than the 0.6% EE. Therefore, in this case, we can obtain the calculated 1.8% EE in the solid phase. Therefore, this anti-L enrichment was enough value to amplify the near enantiomerically pure state. When using R-benzhydrylamine, symmetrical result could be obtained as shown here. And this is a control experiment using non-labeled and racemic labeled benzhydrylamine was used. So 0.6% EE is very small but measurable enantiomeric excess. It is the first example to determine the solubility difference between the diastereomeric isotopomers, difference of the physicochemical properties. First example. Key point is here. These diastereomer crystallize separately because this compound forms conglomerate. Therefore, in the crystallization event, isotope stereogenic center was ignored. So these are separately crystallized. This is a summary slide. So by using the significant amplification at the formation stage of alpha aminonitrile, we have linked with the isotope chirality and highly enantio-enriched amino acid. Next, we move to the circularly polarized light. The strong circularly polarized light was observed in the universe. Therefore, relationship between CPL and highly enantio-enriched amino acid is become the research on the biological homochirality. So we introduced the CPL irradiation to our reaction as shown here. Previously, Professor Inoue reported the asymmetric photolysis of racemic leucine to give L-leucine with 1.3% EE. And Professor Sowai also reported the asymmetric photolysis of racemic asymmetric autocatalyst. After the amplification of EE by the asymmetric autocatalysis, highly enantio-enriched compound could be obtained. And Professor Brigg reported the deracemization of amino acid derivatives using CPL as shown here. We performed our experiment as shown here. To the racemic suspension of the alpha aminonitrile, we have irradiated the CPL at 232 nanometer for 1 day. After the amplification of highly enantio-enriched alpha aminonitrile could be obtained, the CPL was generated using these apparatus. Using the high pressure mercury lamp house system with water filter, infrared was cut off using the water filter. Then 232 nanometer light was extracted using interference filter, and the polarizing filter and quarter wavelength plate was employed to generate the right and left-handed CPL, respectively. The result was summarized in this table. As shown in entry 1, when the racemic suspension of this aminonitrile was exposed to the right-handed CPL, after the amplification of EE, the highly L-aminonitrile with 99% EE was obtained in 48% yield. On the other hand, by the irradiation of left-handed CPL, the aminonitrile with high EE could be obtained as shown here. The stereochemical relationship is reproducible as shown in entry 3 to 6. Next, we measure the solubility and racemization half-life under the photoirradiation in compared with no irradiation as control experiment. As shown here, the under the irradiation, high solubility become high as shown here, and the racemization half-life also become quick as shown here. Next, I will show the circular CD spectrum of this alpha aminonitrile. Because positive CD at the 232 nanometer was observed. L-aminonitrile have the positive CD at this wavelength. Therefore, L-aminonitrile absorbs LCPL preferentially over RCPL. So considering the irradiation of LCPL to the racemic conglomerate, suspension of racemic conglomerate, L-enantiomer absorbs LCPL, then the solubility becomes high, and racemization half-life also rapid. Therefore, solid-to-state D-aminonitrile become large. Then this enantiomer imbalance could be amplified to afford near enantiomer pure D-aminonitrile. So by using the circularly polarized light as a source of chirality, we have synthesized the highly enantiomer enriched aminonitrile by the significant amplification of solid state EE. In combination with the hydrolysis, we have connect with the highly enantiomer enriched amino acid and circularly polarized light. In conclusion, the asymmetric Strecker synthesis was reported here. Finally, I'd like to thank my students and research funding. Thank you.